Hello, in this video I'm going to say a few things about projectiles. There's not actually that much to say because projectiles are just a particular case of two-dimensional motion where you've got one dimension which is horizontal, which doesn't have any acceleration, and one dimension which is vertical, which does have acceleration due to gravity. So it is just a special case of motion in two dimensions. So there isn't much really that we need to say about it. It is just doing two-dimensional suvat. One thing that you can approach slightly differently with projectiles if you wish to, and it can be useful to practice this just as different ways of approaching the same problem, is using parametric equations. You know, we learn parametric equations in our core mathematics, but we don't really use them that much. Projectiles is a prime candidate for actually using them. So how would we set up our parametric equations? So we're setting up equations for x and y as functions of time in this case. So this is where, you know, x and y are our displacements in the horizontal and vertical direction. So we're really using our s equals ut plus a half at squared suvat equation, because if you think again of what this means, this suvat equation, if we write it in a different way, so u plus a half at all multiplied by t, because the displacement is the average velocity multiplied by the time. So there's the time. This is the average velocity because we've got the starting velocity, u, and we've added on half the accumulation of the acceleration, as in half the change in our velocity. So this is, that's just a different way of breaking down what s equals ut plus a half at squared actually means. Average velocity times time, starting velocity plus accumulation of acceleration, all multiplied by time. So if we use that in both directions, horizontal and vertical, then we can get parametric equations for our projectile motion. So we have no acceleration in the x direction, so we're just going to get t multiplied by u cos theta, where u is our starting speed and theta is the angle between the initial projection and the horizontal. So that's what we're going to get for x. For y, we do have the acceleration, so we're going to get a similar starting velocity, but this time we're using sine rather than cosine, and then we're going to take off half of the acceleration squared. Negative because we're measuring y upwards and acceleration downwards, so we have to have a minus g. So they're our parametric equations. We can combine these. You know, we can turn the first equation into having t as the subject, x over u cos theta, and then we can plug that into the second equation, subbing for t, in order to get a Cartesian equation of y as a function of x, rather than having x and y as functions of t. So if we put that in, we're going to get so u sine theta divided by u cos theta is giving us a tan theta. So we've got x tan theta for the first term. And then this one, we're just having a square out. So we're going to have a g x squared over 2u squared cos squared theta. So we can use this general Cartesian format. This is the equation of the parabola that a projectile moves along. So we've got some path of the projectile which is described by this function. It's a negative quadratic because we've got a negative x squared term, and yeah, this just fits in. You know, it's going through y is 0, x is 0, so we're going through a 0, 0 point at one end. And we can make transformations on this if we so wished. You know, we can transform this graph, we can move it up and down by adding on constants, we can shift it left and right, you know, we can do all manner of things with this. But One advantage that you can have of solving this is if you have situations, you've got problems where they're giving you coordinates that points are passing through. So if they've given us u and theta, so we know our initial speed and angle, then this gives us a way of working out pairs of coordinates that the projectile is passing through. If they say, oh, we've ended up at some height above the ground of say 10 meters or something like that, well, then we've got y, we've got theta, we've got u, in which case we can solve for x. We've got a lot of these things that we can do directly in here without having to go to the SUVAT method, because of course in SUVAT we're having to include time in that as part of it potentially. We need, I suppose we only need 3 of these, so we could be leaving out time all the time and solving for the others. Okay, we always know what A is, but maybe we don't have these. We're wanting to look at something on time. We can always get time by going back, having solved this equation, to go back to our parametric equations, particularly this rearrangement of the horizontal component, because that's going to give us time as soon as we've worked out everything else. So this doesn't get used all that much really, because I think when you're going into solving exam questions, normally you want to go for a standardized approach that you know is going to work. You don't want to be messing around with multiple methods, and SUVAT is always going to be something that's going to give you an answer. Okay, you might have to do a couple of simultaneous equations or something like that, but SUVAT is quick and efficient and effective. It's just a little bit faceless at times. There are certain situations when this will be quicker, and again, it's a good idea to keep an eye on these different methods.